Hello, hello. Bismillah. Good morning, good afternoon. So today we will solve the final exam for engineering dynamics. So you read the problems one by one carefully, and always it's a good strategy to start by the easiest problem. So you see here you have 4 questions. Okay, let me skip it, even if it's easy. This is also another interesting problem. 3 questions. Okay, might skip it. This is also another problem. You read it carefully, and you read this one carefully. Might be a long to solve, but this is also a simple problem, but might be a longer one. Oh, okay. This one is the easiest problem. So let's start by it. Okay. Once you have a problem, an exam, you have to have a good strategy. Read everything, and then you start by the easy points. So let me remind you that we have 6 problems. Each problem is 6 points. So let's start by this one. Okay, so we have a disk, and I give you the radius of the disk, 2 meters. So you say radius, which is capital R, 2 meters, centered at O, located in the XY plane. Okay, so that means this is a Z plane. Okay, so the disk is located at the XY plane, let's say on the plane of the paper. So that disk is rotating clockwise. So it's rotating in the negative direction. This is clockwise. At 4 radians per second. So I'm giving you omega. So omega at this time is 4 radians per second. But it's negative, meaning it's rotating clockwise. That's why I drew this clockwise. So the disk is subjected to a constant angular acceleration of 2 radians per second square. You see this in green, in blue here. This is alpha. And it's 2 radians per second square in magnitude. In direction, it's negative. Great. Question, find the velocity and the acceleration of point A. Where is point A? Point A is here. In unit vector notation. First thing first, I will start. There are 2 methods, by the way. Okay? But I will be looking at the vector angular velocity. So it's in magnitude, it's 4 radians per second square. I mean 4 radians per second, sorry, not square. But in the negative direction, so it's minus, so it will be minus k hat. You see, if this is rotating in the xy plane, the vector angular velocity is in the k direction. But because it's negative, you have here a minus. So this is the vector angular velocity. What's the vector angular acceleration, alpha? In magnitude, it's 2 radians per second square. But it's negative, so it's along the direction minus k hat. This is very important. Okay, good. So this, at this given time, this is the angular velocity, and this is the angular acceleration. Now the question is, what is the linear velocity of point A? First, I have to say that A, OA vector is what I will call RA. So this is a vector OA or RA. And we know that it will be what? It's 2 meters because that's the radius in the direction of I hat. You can see it. It's along the direction of I hat. So here you will have I hat. Here you will have J hat, unit vector along, and here you will have K hat, unit vector along Z. Okay, great. Now, if I want to solve my problem quickly, if I know the formulas, basically, you know that the velocity, linear velocity at A is omega plus the position. Okay? So I have to take the angular velocity, which is minus 4 k hat, plus the position, which is 2 I hat. So this gives me minus 8, and I will have k hat plus I hat. What is k hat plus I hat? This is just j hat. So VA, which is the velocity I'm looking for, is minus 8. What are the units? Meters per second. Because it's a velocity, a linear velocity. And in which direction? In the minus j hat direction. So this is VA. In one shot, you get VA. Is it clear? Good. Another way to solve for VA is to say that we know that VA is omega RA. This is a magnitude. The linear velocity is the angular velocity times the distance. So this, what is the angular velocity in magnitude? It's 4. But the distance, it's a radius 2. So it will be 8 meters per second. But what will be the direction? We know that if I'm rotating clockwise, the velocity at A is always in the direction which is tangent to the circle. The velocity is always tangential. So VA is here. Okay? And the magnitude is 8 meters per second. So VA is in the negative y direction. So VA vector has a magnitude 8 meters per second, and it's in which direction? Negative y direction, basically negative j hat. And it gives you exactly the same answer. Okay? You can pass by this formula, or you can use the fact that you know that linear velocity is r times omega, and you calculate it in magnitude, and the direction, you get it by exploiting the problem, knowing that the velocity is always tangent to the circle, the path, and it's in the, here, it's in the minus j hat direction. That was for VA. You do this, you have half of the point. Great. Now let's move to the next question, which is the acceleration at point A. You can use a formula also. You can say acceleration of at point A is a derivative of the velocity at point A with respect to time, which is a derivative with respect to time of this omega cos r. If you remember this, we already solved this actually. This will give you this formula. Will give you alpha A plus r minus omega square r. So acceleration at point A is alpha A times RA minus omega squared times RA. Let's do the calculation. So alpha A, we already know alpha A, minus 2 k hat. RA, we already know RA, 2 I hat, minus omega squared, 4 squared, RA, which is 2 I hat. So we will have minus 4 k cos I. That gives you j hat minus 16 times 2, that's 32 I hat. So A is minus 4 j hat minus 32 I hat meters per second squared. You can write it this way if you want, minus 32 I hat minus 4 j hat meters per second squared. Is it clear? Yes. So you need to know also this formula. And most formulas are in the formula sheet. Now, if I don't want to use this, I can use the fact that the acceleration here of point A will be made up from two accelerations: the tangential acceleration and the normal acceleration. If you remember, the magnitude of the tangential acceleration is r alpha. So r is 2, alpha, we already know it's 2, so the tangential acceleration is 4 meters per second squared. What will be the direction of the tangential acceleration? The tangential acceleration, if I want to put it in vectors, it's 4 meters per second squared. It is in the direction of minus j hat. We know it because this direction here is the negative y direction. So the tangential acceleration is minus 4 j hat units are meters per second squared. Okay, you know this. Now the second component is the normal acceleration. The normal acceleration, you know that it's v squared over r, or r omega squared. R is 2, omega squared is 4 squared, and this gives me 32 meters per second squared. Now what's the direction of an? So the magnitude is 32 meters per second squared. What's the direction? You see here? You see it from the figure. It has to be centripetal. So it's negative I hat. My total acceleration is made of a tangential plus normal acceleration. So this will be minus 4 j hat minus 32 I hat, and the units are meters per second squared. So this is AA, and it gives you the same answer, of course. So be very careful. I have noticed many students like Kevin, Yasin, and I don't remember who else. Adding vectors is different from adding scalars, okay? Be very careful when you add vectors. You know that already. Maybe you were stressed because of the exam. I will come back to this later. So VA is minus 8 meters per second j hat, and AA is minus 32 I hat minus 4 j hat meters per second squared. This is AN, and this is AT. So if I want the magnitude of AA, some of you, they will add AN plus AT, which is utterly false. If you want the magnitude of the linear acceleration at A, you have to take the square root of the sum of the square. I will come back to that because I notice many students are mistaking adding vectors and adding scalars. So that was for this very simple exercise. You do this and you have 6 out of 6. Okay. Those who got it right, I give them bonus points. Next question. I can start by this question also, which is easy. Read it carefully and then we start solving it. So this motor, by motor I mean this one here. Okay, this motor that you are seeing here is used to turn wheel B. You see wheel B is here via a pulley A, and pulley A is here. Okay, this is a pulley A, as you can see. And what the radius of pulley A is 15 centimeters. So this is RA. And what is the radius of wheel B? The radius of wheel B, RB, is equal to 0.4 meters. Good. So the pulley A, which has a radius of 15 centimeters, is connected to the motor, as you can see. So the pulley A connected to the motor begins to rotate from rest. So I know initial omega A. Omega A0 is 0. Do you all agree? Great. So it starts rotating from rest. So omega A0 is 0. But with a constant angular acceleration of alpha A. So we have alpha A, which is a constant. So we have constant acceleration motion. constant angular acceleration motion. So this is 2 radians per second squared. Okay, and it's constant. Before reading the question, let me exploit the data of the problem. So here we have a pulley. Okay. So we have a conveyor belt connecting A and B. Of course, this conveyor belt or the transmission belt does not slip. What are the different relationships I know if I have 2 pulleys connected by a transmission belt? 3 equations, write them down. RA times theta A is equal to RB times theta B. We all remember that, okay? Second relationship, RA times omega A is equal to radius B times omega B. And third relationship, RA times alpha A is equal to RB times alpha B. So theta, you know the radius, the radii, RA and RB. Theta as the angular displacement. So there is a link between the angular displacement for A and the angular displacement for B, and the link is this, meaning here if I want theta B, it will be theta A times RA divided by RB. We all agree with that, okay? Great. If they had the same radii, the same radius, the angular displacement for both the wheel and the pulley will be the same, okay? Now, the bigger radius will have a smaller what? Smaller omega, or smaller theta. So here also we will have omega B. It will be omega A times RA divided by RB. And alpha B will be equal to alpha A times RA divided by RB. Okay, these are very important equations that we already demonstrated in class, and you are aware of them. Okay, great. So here we will have constant angular acceleration. So you see, if alpha is constant and is equal to 2 radians per second, so we can calculate alpha B. Alpha B also will be constant. It will be alpha A, 2 radians per second square, times RA is 0.15 divided by RB, which is 0.4. So I can just put 15 divided by 40. So this will give you an alpha B, and it's constant, and it will be 0.75 radians per second square. So alpha B, which is a wheel B, will rotate counterclockwise with a constant angular acceleration alpha B, which is 0.75. We all agree with that? Okay, good. Now let's read the question. So the question is, I want to find the magnitude of the velocity and acceleration of point P of the wheel. So the point P here, this is what I want. I want to know the magnitude of the velocity of point P, and I also want to know the acceleration, the magnitude of acceleration of point P. But I want to know the magnitude of the velocity of point P and the acceleration of point P when? After the pulley A has turned 8 revolutions. This pulley A has turned 8 revolutions. Basically, I'm telling you that theta A should be 8 revolutions or 8 rotation. So 8 rotation is 8 times 1 revolution, and 1 revolution is 2 pi radian. So theta A is 16 pi radian plus theta A. So if pulley A has turned by 16 pi radians, 8 revolutions, how many revolutions the wheel B will turn. Of course, you will use it here. So I say that theta B is theta A, which is 16 pi radians, times RA, which is 15, divided by RB, which is 40, or 0.15 divided by 0.4. And that gives you theta B. So how much will you get? Theta B is just free revolution, which is basically 6 pi radians. So theta B, write it down, is 6 pi radians. 6 pi radians. Okay, great. Now, okay, let's solve our problem. We want VP, the velocity at this point here. So the velocity at this point will be in this direction, but I don't care about the direction. I just want the magnitude. I said it clearly. So what is the magnitude of the velocity at point P? VP is R C omega D. What is RP? RP is the radius, that's RB, omega B. So what is RB? 0.4. Now what is omega B? After 8 revolution. Okay, after 8 revolution, I can calculate omega B. I want omega B after 8 revolution. How can I calculate it? Easy. We have a constant angular acceleration. So omega B will be omega B0 plus alpha T. What is omega B0? Omega B0 is 0. Let me write it down in this way. Omega B0 is 0 because omega A0 is 0. They both start from rest. But here you see, I cannot use this because I don't know the time. Okay, so I will not use that. As I told you, I want omega B after 8 revolution, but I did not give you the time, so you will not use this one. Which other formula do I know when I have constant angular acceleration? I know that omega B squared will be omega B0 squared plus 2 times alpha B, theta B minus theta 0. So basically this is delta theta B. But I already know delta theta B. Delta theta B is 6, is theta B basically. This is theta B. So this is 6 pi radians. Omega B0 is 0, forget about it. So basically I will have omega B is just square root of 2 times alpha B that I know times theta B that I know. So this is square root of 2 times, what is alpha B? 0.75. What is theta B? We already calculated it. It's 6 pi. When you do the calculation, and you will find that omega B is equal to what? 5.32 radian per second. And that's omega B. So let me write it down here. Omega B is 5.32 radian per second. Once I know it, I will plug it here. After 8 revolution of A, meaning after 3 revolution of B, I will have omega B equal to this. So basically VP is 0.4 times 5.32. You do the calculation and you will find 2.13 meters per second. So VP, which is what I want, VP is 2.13 meters per second. Is it clear for everyone? Okay. You start by these equations, and then you exploit the fact that we have constant angular acceleration for A, meaning I will know constant angular acceleration for B. If I know the angular displacement for A, I will know the angular displacement for B using this relationship. If I know omega A, I will know omega B using this relationship. If I know alpha A, I will know alpha B using this relationship. And then I will use my regular equation to know what is my VP. Don't forget, if we have constant angular acceleration, let me just clean the sheet. If you have constant angular acceleration, you have your three formulas. You remember the three formulas. Alpha is constant. So omega at any time is omega 0 plus alpha t. That's equation 2. What is equation 1? Equation 2 will be basically theta at any time is theta 0 plus omega 0 t plus half alpha t squared. And equation 3 is omega at any time squared is omega 0 squared plus 2 times alpha delta theta. Okay. We have used this one because I did not give you the time, but I gave you delta theta. So you can know what is omega after 8 revolutions. Okay, great. Next. So we already know VP. So let me write it down again. VP is 2.13 meters per second. And it's equal to RB omega B. We already calculated it. Now, what about the magnitude of the acceleration? Well, we know that the velocity is purely tangential. So you only have one component of the velocity, which is the tangential velocity. But the acceleration at t has two components, the tangential acceleration plus the normal acceleration. What is the tangential acceleration? The tangential acceleration in magnitude will be r b times alpha. Because I'm looking at this point P. So it will be 0.4 times alpha b. So it's 0.4 times 0.75. What is the tangential acceleration? You do the calculation and you will find that the tangential acceleration is 0.3 meters per second squared. That's the tangential acceleration here. It will be in this direction. What about the normal acceleration? The normal acceleration, the magnitude of the normal acceleration is omega square r. So we already calculated omega b squared r b. What is omega b squared? We already calculated omega b is 5.32 squared times rb, which is 0.4. You do the calculation and you will find 11.32 meters per second squared. And the normal acceleration is the centripetal. It's the centripetal acceleration toward the center. So this is the normal acceleration. So now if I want the magnitude of the acceleration, some of you, they just took, I want the magnitude of the acceleration at p. Some of you, they just added AT and AN, which is utterly false. You see that AN and AT are not in the same direction. They are making an angle of 90 degrees between them. And AP is a vector. So basically, if I want AP, just square root of A tangential squared plus A normal squared. Okay, don't add components to get the magnitude. You know that already. I know that you know that. Maybe you were too stressed. So I think some of you did it out of stress. So basically, you do the calculation and you will find that the acceleration is roughly 11.32 meters per second square. Why? Because this is high, but this is constant and it's small. Basically, this will dominate. Okay? So that's the magnitude of the acceleration. So the tangential acceleration is small, but the normal acceleration is quite high, actually, which is the centripetal acceleration. So in magnitude, the normal acceleration dominates is bigger than the tangential acceleration in magnitude. So the total acceleration is more or less more normal than tangential. That's it. You solve this problem, you have 6 points, 6 out of 6. Now, step by step, I will grade each step. So if you understand what's going on, and then I will give you your answer, and I give you your points. So these 2 problems were the easiest. Now let's move to the next problem. Okay, so for this problem, number 4, not a difficult problem, maybe it's long, but you can solve it. You have solved these type of problems in class. So we have 2 disks, A and B, and I give you the mass. So the mass of A, so this is the first disk, and the mass MA is 3 kilogram, and MB is how many? 2 kilogram. Okay, so this is MA, and this is MB. And they are sliding on a smooth horizontal plane with the velocity shown. You see here the velocity of A, this is VA, and this is velocity of VB. VB. So I will call VA1 and VB1. Okay, right. So this is the velocity just before impact. Question, I want the speed just after impact. If the coefficient of restitution is 0.7. So this is given here. And this is the line of impact. And this is a plane of contact, normal to the line of impact. Okay, so if I call the line of impact X prime, the plane of contact, I would call it Y prime. And it's normal to the line of impact, and you have 90 degrees between them. Do you all agree? Okay, good. Now what I will do here is I know that VA, I will call before impact, I will call it 1, situation 1. And after impact, I will call that situation 2. So let me write the velocity of A before impact, VA1. You can see it here, minus 10 meters per second I hat. So this is the unit vector I hat, and this is the unit vector J hat. So I hat, and this is J hat. Let me take another pen. Now you can see that VA1 is minus 10 I hat. What about VB1? Well, VB1 is plus 8 meters per second I hat. Okay, you can see it. Great, but I don't want to express them in X and Y. I want to express them in X prime and Y prime. I want to express these velocities in the line of impact and in the plane of contact. I have to do a coordinate transform. I have to transform the coordinate. So here I will first say that this line of impact, I will call it the direction X prime. It has a unit vector, and what the unit vector along X prime, I will call it I hat prime. And the unit vector along Y prime, I will call it J hat prime. So now I want to express I hat and J hat in I prime hat and J prime hat. Well, I know that this angle here is the angle theta. I will call it the angle theta. And cosine theta is given here. The angle theta is here. So cosine theta is 3/5 is 0.6. Sine theta will be 4/5. Is 0.8. And tangent theta is equal to what? I don't need it. Anyway, let's just write it down. Is 4/3. So all this will give you an angle of 53.13. 53.13 degrees. So theta is 53.13 degrees. But as you will see, all what I need is cosine theta and sine theta. Now we can say, as you know, we studied this extensively. I can write the vector I prime hat in terms of I and j. So this I prime hat, if I project it along I hat, I will have cosine theta I hat plus sine theta j hat. And j prime hat will be minus sine theta I hat plus cosine theta j hat. So this is what we summarize in this table. You remember? I can write it this way. I prime hat. And here I will put j prime hat. And here I will put I hat. And here I will put j hat. So I prime hat will be cosine theta here. Sine theta here. And here j prime, I'll have minus sine theta. And here I will have cosine theta. Okay. This is a rotational matrix, as you can see. Cosine theta on the diagonal, sine theta, and minus sine theta on the off diagonal. So, well, this just means that I, and you could have written this easily if you want, I hat is cosine theta I prime hat minus sine theta j prime hat. And j, I'm just reading from this. So I is cosine theta I prime hat minus sine theta j prime hat, and j is sine theta I prime hat plus cosine theta j prime hat. Okay. So in other words, if I want here and I want to write VA1, but I want to write it in I prime hat and j prime hat. I want to express it along the line of action and the plane, the line of impact and the plane of contact. So I'll say it's minus 10. Now I will replace I by which value? By this value here. Right? So cosine theta, which is 0.6, I prime, minus sine theta, which is 0.8, j prime hat. In other words, VA1 is minus 6 I prime hat, plus 8 j prime hat. I can do the same for VB1. It will be minus 8, and then I replace I prime by its value is 0.6, 0.8. So VB1 before collision is equal to what? 4.8 I prime minus 6.4 j prime. Hey, this should come quickly, okay? And you know this already, so you need to practice this. Now let me tell you a few things here. Let me take the red pen. So this is what I will call VA1 X prime, the X prime component of V1 before collision. And this plus 8 is what I will call VA2 Y prime, the Y prime component of VA1, because we are still in 1, we are still before collision, okay? So this, I will call it VB1 X prime, and this, I will call it VB1 Y prime. Is it clear? Okay, good. Now, after collision, I will have VA2, but I will have it in the X prime, Y prime direction. Basically, I will have VA2 X prime, and then I will have VA2 Y prime. Then I will have VB2, which will be VB2 X prime, and I will have VB2 Y prime. Now the question is this: find me these four components, and then you get the speed VB2 in magnitude and VA2 in magnitude. So the game is to find these four components. Let's get them now. So that's what we have to do, okay? Great. I will write the main results, and then we will proceed in solving. Now my paper is quite busy and messy, but you understand the game. Okay, let's look at it. So this is what I did before collision. So this is before. This is what I know. I know that VA1 has two components, -6 I hat prime, -8 or +8 J hat prime. Don't make a mistake in the signs. Please be careful. Okay? And VB1 is 4.8 I hat prime -6.4 J hat prime. This is before. Now after, I call it 2, situation 2. I will call it now VA2. Now VA2 will be what? Let me write it this way, okay? I will have VA2 X prime, and then I will have VA2 Y prime. And VB2, you will say VB2 X prime and VB2 Y prime. Great. To be consistent with my notation, let me just call this. This is -6. This is VA1 X prime +8. This is VA1 Y prime. And this is 4.8, which is VB1 X prime -6.4, which is VB1 Y prime. Okay? Great. Now the game is to find this guy here, this guy here, this guy here, this guy here. What should we do? You know that along the line of action, so this is the line of impact, not line of action, I mean line of impact. This is the line of impact, and this is the plane of contact, normal to the line of impact. This I'll call it Y prime. This I call it X prime. So along X prime, which is the line of impact, we have conservation of momentum. Okay, conservation of total momentum, meaning momentum before collision is equal to momentum after collision. along x prime, meaning, let's write it down. MA VA1 x prime plus MB VB1 x prime. This is momentum before collision along x prime. So this should be equal to momentum after collision, MA VA2 x prime plus MB VB2 x prime. Let's put the numbers. Okay, let's put the numbers. MA is 3. VA1 x prime, this is minus 6. MB is 2. We all agree. VB1 x prime is 4.8. Do the calculation without making a mistake. This gives you minus 8.4. So minus 8.4 is equal to 3 times, if I call this alpha, is 3 times alpha plus 2 times beta. And I have my first equation. So this is what I call alpha, and this is what I call beta. So this here is what I call alpha, just for to, not to have these subscript all the time. And this is what I call beta. Okay, so I have a first equation. Good. Coming from conservation of momentum before and after collision along the line of impact, which is x prime. Second equation will come out of the coefficient of restitution. So still along the line of impact, I will use the coefficient of restitution, E, which is 0.7. We remember the formula of coefficient of restitution is relative velocity after, basically. VB2 x prime along the direction of line of impact minus VA2 x prime divided by what? VA1 x prime minus VB1 x prime. So this is beta. This is what I call beta, by the way, minus alpha. This is what I call alpha divided by VA1 x prime. That's why don't make a mistake in the signs. Because if you make a mistake in the signs, everything is lost. VA1 x prime. What is VA1 x prime? It's minus 6. Minus VB1 x prime. What is VB1 x prime? It's 4.8 or minus 4.8. So in other words, I will have beta minus alpha is 0.7 times minus 10.8. Do the calculation and you will find this is equal to minus 7.56. Okay. So Aliu, my brother Aliu, he said minus 75.6. I guess he multiplied by 7. No, it's 0.7, Aliu. Okay. So apart from that, you got everything right in this question. Yes. A mistake problem or an attention problem. Okay. So it's minus 7.56, not minus 75.6. Great. So the second equation is basically minus alpha plus beta is minus 7.56. So this is equation 2. You know how to combine them, right? Okay, you combine them. You know how to solve system of equation with 2 unknowns. You will find that alpha, I will not do it. You know how to do it. So alpha is equal to 1.344, and this is VA2 x prime, and beta, which is VB2 x prime, if you do the calculation, is minus 6.216. Okay, these are, so I know here and I know here. Now, along the plane of contact, along y prime, for each particle, you will have conservation of momentum, meaning the velocity will be the same, meaning VA2y prime is equal to VA1y prime. In other words, it's equal to +8. And VB2y prime will be VB1y prime, which is equal to minus 6.4. I have solved my problem. I know everything now. Meaning after collision, which is the situation 2, for A, which is the particle A, I will have VA2. She will have two components. 1.34, which what I called alpha, and then I will have 8. And B has two components, VB2, the velocity, which are minus 6.216 and minus 6.4. If you know the components, now you can know the speed. VA2 is square root of this squared plus this squared. And VB2 will be square root of this squared plus this squared. By this, I mean this here, this, put it here. So I got VA2 in speed is 8.11 meters per second. And VB2 in magnitude is 8.92 meters per second. These are the speed after collision, respecting these constraints. Is it clear? So no need to come back to bring it back to the XY. The speed will be the same. Does not depend on the reference or the frame. Okay, good. So that's the answer. And it makes sense. I started with initial speed of 8 and 10. I end up with final speed of 8.11 and 8.9. Good. Now let's move to the next problem, which is extremely important. So in this problem, you have to read carefully and then we solve it. Not that complicated. So we have ball A, and MA is 2 kilograms, and MB is 0.5 kilogram. So you can say that if MB is M, MA is 4 times M. So this will help us simplify the problem. So ball A that you can see here is dropped from rest. So VA initial is 0, dropped from rest. It slides down a smooth trench and strikes another ball which is resting. So VB initial is also 0, VB 0. So VA 0 is 0 and VB 0 is 0. Question, determine this height H from which ball A should be released so that after direct impact, head-on collision, ball B just barely leaves the circular surface. So ball B will go up and then reach here, and it barely leaves here. So we can say that the VB final here, VB final, should be 0. Now I give you the coefficient of restitution, which is 0.8. In order to solve this problem, you have to be sequential, step by step. First, let's find the velocity of A just before collision. So I will call that VA1. Okay, in order to get VA1, it's easy. There is no friction. Ball A is at height h. So you know that the potential energy of ball A is, basically I use conservation of mechanical energy. Delta E is 0, meaning mechanical energy at 0 is equal to mechanical energy at 1 for A. What is the mechanical energy at this position here? 0 kinetic energy plus MAGH. What is the mechanical energy here? If I choose this to be my datum, so this is my datum for the reference, the ground. Okay? So kinetic energy will be half mVA1 squared, and gravitational potential energy is 0. Basically, I'm transforming MGH into half MAVA squared. You simplify by MA, and you know what you know already. VA1 just before collision is equal to square root of 2GH. So that's the velocity of A here. Okay, so we know that the velocity before collision for A, VA1, is equal to square root of 2GH, but I don't know H, okay? I keep it. What the velocity of B before collision? It's at rest. That's what I call VB0. Yeah. Now, I will say that I have collision and direct collision or direct impact between A and B. I will have conservation of momentum. Momentum before, which is MAVA1 plus MBVB1. By the way, VB1 is 0, so this is 0. Forget about it. This should be equal to what? MAVA2 plus MBVB2. Is that clear? So let me put the numbers. MA is 4M. VA1, which is just square root of 2GH plus 0, is equal to MA, which is 4M, VA2 plus MB, which is M, VB2. Let's simplify by M. So we will have this equation here, and we will write it down. 4 times square root of 2GH, so that's VA1. This is equal to 4 times VA2 plus 1 time VB2. So I have a first equation. How many unknowns? I don't know VA2, the velocity of A after collision. I don't know VB2, which is the velocity of B after collision. And I don't know also H, but it's okay, I can know them. So I have exploited the first information, then the collision. Now I will exploit the second information. I will put it in red. So that's very simple. Now this B here, after collision now, will have a velocity. And that velocity, I call it VB2. It is not 0 anymore. Now there is no friction. It goes up and it reaches a height of 2 meters, 0.2 meters. So we can also use conservation of mechanical energy. So at the beginning, I have half MB VB2 squared and 0 gravitational potential energy. And I transform everything into height, which is MB GH. But this H is 0.2 here. I simplify by MB. So this will give me VB2. So VB2 will be just square root of 2G times 0.2. We can do the calculation if you want. Square root of 2 times 9.81 times 0.2. This will give you VB2, which is the velocity of B just after collision, of how many? 1.98 meters per second. So this velocity of B will help me to barely leave the circular surface. The circular surface here, meaning the VB final here will be 0. Okay, so VB2 is 1.98 meters per second. Let me just put it to 981, by the way. 981. 1.981. Okay, so I will come here and then I will plug it here. So this equation will become what? This equation will become 4 times square root of 2GH is equal to 4 times VA2 plus, let's say, square root of 2G times 0.2. I just took equation 1 and I replaced VB2 by its value. So we have this equation here, which is just another version of equation 1. So you write it down. Now my unknowns are what? VA2 and H. Now how can I find another equation? You use the coefficient of restitution, E, which is 0.8. By definition, E will be VB2 minus VA2 divided by VA1 minus V minus VB1. Remember, what is VB1? Just before collision, what was the velocity of B? It was 0. So this is equal to 0. What is VA1? Just before collision, is square root of 2GH. VA1 is just square root of 2GH, as you can see it here. So if I exploit this, I will say 0.8 times square root of 2GH is equal to VB2. By the way, what is VB2? I know it already. It's this, 1.981. So it will be VB2 minus VA2. Let me rewrite all this in a cleaner form. First equation is this equation here. 4 times square root of 2GH is equal to 4 times VA2 plus VB2. We already showed that VB2 is just square root of 2G times 0.2. And we calculated it, 1.981 meters per second. Let me just keep it as it is. So this is the first equation. And if you remember, it came from conservation of momentum before and after collision. And it came from the fact that the first A is coming from a certain height, and you transform all the potential energy into kinetic energy, and B, the other way around, goes from totally kinetic energy to a potential energy, which goes high to a height of 0.2. So that's the first equation. Second equation, we used the coefficient of restitution. We said that 0.8 times square root of 2GH is equal to what? VB2 minus dA2. So this is equation number 2. Okay. Now let's say, for instance, I want to get rid of VA2. So I will say equation 1 plus 4 times equation 2. 4 times equation 2. So I take equation 2, I multiply by 4, and I add up. So this will give you this. 4 plus 0.8 times 4 square root of 2GH. So here I'm multiplying this by 4. You see, when I add this and this will go away. So here I will have this plus 4 times this. So I'll have 5 times VB2. In other words, I will have 7.2 times square root of 2GH. This is equal to 5 times VB2. What is VB2? It's square root of 2G times 0.2. Let me take the squares. 7.2 squared times 2GH is equal to 5 squared times 2G times 0.2. Let's simplify by 2G, and you will have that H will be 5 squared divided by 7.2 squared times 0.2. You put everything and you calculate that H, it will give you 0.096 meters. That's H. I did it this way. You could have done it another way. You will find the same answer, obviously. So H, which is the height from which ball A should be released so that after direct impact, ball B just barely leaves the circular surface. That height H is 96 millimeters. Yeah. Is it clear? Nice. Let's go to the next problem. So it was not difficult. You just need to read it step by step and you will find the right answer. And many of you found it. So congratulations. Let's move to the next problem, which is problem 2. So in this problem, we say that we have a 2 kilogram collar. So the mass is 2 kilograms. Is released from rest at A. So let's assume that A is here. Okay. Well, let's put it this way. A is here. And V initial is 0, released from rest. And slide down this inclined rough rod, and I give you the coefficient of kinetic friction, mu K, 0.4. Question, calculate the velocity V of the collar just before it strikes the spring. The spring is here. So let's draw the horizontal here. So this distance here is D, and I'll call it 0.5. Okay, so that's 0.5. Question is, what is the V final of the collar? V initial is 0. What is V final? So we can use either change in mechanical energy, is work of friction, or I can say change in kinetic energy is equal to network. Okay. This is the initial state, and this is the final state for state 2. Change in kinetic energy is equal to network. So what is change in kinetic energy? It's half mass V final squared minus half mass V initial squared, which is 0, is equal to network. Now network is, first let me draw a free body diagram. Let's say my collar is here. First you have the weight of the collar. I'll call it Fg, which is the gravitational force. Then I will have the normal force, which is normal to this. I'll call it Fn or N if you want. Then I will have the frictional force. And it's Fk. Let me repeat what I just said. The free body diagram. Okay, so is it working? I have the weight vertically downward, Fg, and I have the frictional force in the direction opposite to the motion, and I have the normal force from the rod, from the collar. So of course, my system is a collar of mass m. This is a free body diagram acting on it. So the network, I have to calculate the work of the gravitational force. The work, I can call it W or U, depends on you. Work of frictional force, Fk, plus work of the normal force, Fn. These are the different forces. You know that Fn is normal to D. Where is the displacement? The displacement is this, vector displacement. So basically the work of the frictional force, of the normal force is 0. Forget about it. What is the work of the gravitational force? It's plus mgh. H being this is H. The change in height, just d sine theta. So H is d sine theta. I know, by the way, d is 0.5 meters. And the work of the frictional force is minus mu k Fn d. So I have plus mg d sine theta minus mu k. What is Fn? Fn is, you remember correctly, Fn. So I did not talk about it, but this is kind of an incline. So theta. So you see that that angle theta is coming back here. Okay. So you see that if I use, so this part here is mg cosine theta. So Fn is mg cosine theta. Okay. And this part here is mg sine theta, but nothing. Okay, and this should be equal to half m v final squared. So we simplify by m, and you find that v final is equal to square root of 2gd sine theta minus mu k cosine theta. We know everything. To 9.81. D, we said it, 0.5. Sine theta is sine 60 minus mu k 0.4 cosine theta, which is cosine 60. And we find that V final just before it strikes the spring, which is the velocity just before it strikes the spring, is 2.56 meters per second. So the velocity when I reach here, when the color reach here, is 2.56 meters per second. So that was the first question. Yeah? We could have used this, but we prefer to use work kinetic energy theorem. It gives you the same answer. Okay, good. Now, next question. What is the maximum compression length? Find the maximum compression length, X, of the spring. Now, when it hits it, it comes with a kinetic energy. It will compress it until the spring is here, for instance. So this extra distance here I'm covering, which is a maximum compression length, X. Of course, X is positive because it's a distance. There's that maximum compression length, X. At maximum compression, the V final will be 0. It will stop. And the question is, what is that X? Okay, what I will do is, instead of using the velocity just I choose before, meaning instead of using from this state to this state, I will use from the initial state to maximum compression. This will make sure that if I make a mistake in the velocity, it will not appear. Okay, so I will start from A. I will look at two situations. The initial situation is when I'm at A, and the final situation is when I'm at maximum compression. So what is the initial kinetic energy? Is 0 because the initial velocity is 0. The initial speed, it dropped from rest. What is the final speed at maximum compression is 0, so the final kinetic energy is 0. So I will be using work kinetic energy theorem. I'll say delta K, which is 0, is equal to the network. Now, what is the work applied on my system from A to the maximum compression? I will need the work of gravitational force. I will need the work of normal force, which is 0, by the way. Plus, I will need the work of frictional force, but also I will need the work of the spring force. Now, what's the work of the gravitational force? Okay, the work of the gravitational force will be mgh. But here h will be, so if this is d plus x, so h is d plus x sine theta. So mg, d plus x, d is 0.5 plus x, and I don't know x, sine theta, which is sine 60 degrees. This is the work of the gravitational force. The work of the normal force is 0. Now, what is the work of the friction force? The work of friction force is minus mu k Fn, which is mg sine theta, mu k Fn d. But the d here is d plus x, basically 0.5 plus x. Because the friction will apply from A along the rod until maximum friction. So the new d here is d plus x, which is 0.5 plus x. Now, plus, don't forget the work of the spring force. The work of the spring force is half k x initial squared, which is 0 squared, minus x final squared, which is x squared. That's what we have to solve. Let me write it in a clear way. I have to find 0. mg, I can calculate it. M is 2. G is 9.8. So let me calculate mg sine theta. If you do the calculation, you will find 17. I'll have 17. I just calculated mg sine theta. 17 times 0.5 plus x plus or minus mu k. What is mu k? 0.4. Now mg cosine theta, if you do it properly, you will find 9.81. mg cosine theta is 9.81. So this is 9.81. And then I multiply by 0.5 plus x. Now here I will have minus half k, which is 1,600 x squared. And this has to be equal to 0. So this is what I have to solve. Let me distribute, put the constant together, put the x squared together, put the x's together. I'll find something like 800 x squared minus 13.07 x minus 6.534 is equal to 0. So this is a quadratic equation I have to solve. Or just x squared minus 0.0163x minus 8.167 10 to the power minus 3 is 0. It's the same. I just have divided by 800. So you know how to solve this quadratic equation. You know how to solve this quadratic equation. They give you exactly the same result. I will have x is 0.099 meters. In other words, it's 9.9 centimeters. So that's the maximum compression length. So the second one, the second root of this quadratic equation is negative, minus 0.083. Of course, this is not an acceptable solution because x is a distance. It has to be positive. So the answer is 9.9 centimeters. Great. Now for the last question, I remove it. Okay, you don't need to answer it. The maximum velocity, forget about it. Not the maximum velocity of the collar. Okay? You can think about it, but not important. Maximum velocity will happen when the acceleration is 0. So the acceleration is the derivative of velocity with respect to time. So velocity will be max when the acceleration is 0. So you can write it down if you want, and then you find the position that will give you that. And then you will calculate the velocity that will give you that. So we don't need it. By the way, because of this question, I give a bonus point to everybody. I know that you wasted time on it, but it's not important. I give you +2 to everyone, just because of the last question, which was not important. Okay, now let's go to the last problem, which is very important. So read the question carefully, and then we solve it. So for this last problem, which is quite straightforward, we have a particle of mass 2 kilograms, which slide down along a smooth circular path of radius 3 meters. So this radius is equal to 3 meters, and the particle started from here. So we said it here. Basically, the particle starts moving from rest point A. At point A here, S is equal to 0. S is the length of the arc, and theta is 0, and the velocity is 0. It started from rest here. Question: for any theta, draw the free body diagram and write Newton's second law in the tangential and normal direction. Let's assume that I cover an angle theta, and then later you see I will say that the angle theta is 60 degrees. But for the time being, let's just take any angle theta. So I sweep an angle theta, meaning that I went for an arc S, which is radius times theta. S is equal to r theta, if you remember. Now my particle is here. Let me draw a free body diagram on the particle. First, I will have the weight of the particle, which is a gravitational force vertically downward. This is Fg, and the magnitude of it is mg. Then I will have the normal force, or the normal reaction, whatever you call it, and it's normal, meaning the radially inward here. I call it Fn. Did I forget something else? There is no friction. So there is no friction. So this is a free body diagram. We can make it more beautiful by looking at the tangential direction. This is a tangential direction. Okay, that's the tangential direction, and this is the normal direction. This is n, and this is t, the tangential direction. And between the tangential direction and the normal direction, obviously you have 90 degrees. Great. So the system is a particle of mass m. We have drawn the free body diagram. Only two forces: gravitational force, which is down, and normal force, which is on the normal direction. Newton's second law, weight plus normal force is equal to ma, plus the Newton's second law. So let's project it along the tangential direction, and let's project it along the normal direction. Now, along the tangential direction, let's see where the angle theta is coming again. Remember, if I have the angle theta here, the vertical is perpendicular to this, and the tangential is perpendicular to the normal. So the angle theta is coming back here. Be very careful. If you make a mistake here, you lose everything. Okay, is it clear? The angle theta is coming back here. So if I project this along the normal direction, I will have plus mg cosine theta. So this here is mg cosine theta. So the angle theta is coming here. And this here is mg sine theta. Don't forget the minus. We'll come back to it. Okay, so along the tangential direction, it's mg cosine theta. Many of you made this mistake because they made a mistake in the angle theta. So the angle theta is coming back here. Okay, that means it will be mg cosine theta. What's the normal force along the tangential direction is 0. And this has to be equal to ma tangential. Let's simplify by m, and you will find that the tangential component of the acceleration is g cosine theta. Is this a constant acceleration for the tangential direction? No, because this theta varies. Okay? It's not like an incline where theta is fixed. This is different from a constant. So the tangential acceleration is not constant. So don't use the constant acceleration equation. Okay? Theta was 0, theta will be 60, theta will be 90, etc., etc. So it's not a constant. Great. Now I will use Newton's second law, and I will project it along the normal direction. What is the normal component of the gravitational force? As we said, it's minus mg sine theta. Why? Because this is what I want. The normal direction is inward. This is here, so it's minus opposite sign, so minus mg sine theta. Plus the normal force Fn, and this has to be equal to man. So that means that the normal force Fn is m. an, you remember that the normal acceleration is v squared over r. So it will be m v squared over r plus d sine theta. This is the normal force. Okay, great. So we have drawn the free body diagram and we wrote Newton's second law in both the tangential direction and normal direction. Now question B, determine the velocity, the tangential and normal acceleration when theta is equal to 60 degrees. Now theta is equal to 60 degrees. So A tangential will be G cosine 60 degrees. You can calculate this. It will give you 4.91 meters per second squared. Okay, this is a tangential acceleration. It's not a constant. Instantaneously, this is a tangential acceleration. For any theta, I have a new tangential acceleration. Good. So this is a tangential acceleration at 60 degrees. What about the normal acceleration, an? It should be velocity or speed squared divided by r, and r is equal to 3. But I have to get the v squared. V squared meaning v at theta equal to 60 degrees squared divided by r. Well, let's get v first. Once I get v, I will know the velocity, because the velocity is purely tangential. Now let's get v. How do we get v? Very simple. You remember that the tangential acceleration is d cosine theta. But you also remember that the tangential acceleration is v dv over ds. In other words, A tangential ds is v dv. This is one of the kinematic equations. So that means g cosine theta ds is v dv. But you remember, s is r theta, meaning ds is r d theta. So I'll replace this s ds at g cosine theta r d theta equals v dv. Now, if I want the v at 60 degrees, I will have to integrate. Okay? I have to integrate here because you see here my theta is going from 0 to 60 degrees. In order to do that, that's why I have to integrate. Okay? The theta is not constant. So I will integrate between 0 and 60 degrees. And here the velocity goes from v0 to v60 degrees. Let me put the constant outside. I will have gr, and I will integrate cosine theta d theta. So what's the integral of cosine theta? That will give you sine theta. And I will take it between 0 and theta, which is 60 degrees. And the right-hand side, this gives me half v squared between v and 0. This half v squared. In other words, v squared is 2 times gr sine theta. This is v squared. So if I want v60 degrees squared, it will be 2 times gr sine 60 degrees. Let's calculate it. Gives me 50.97 meters squared divided by second squared, meaning v60 is equal to 7.14 meters per second. So that's the speed. So at theta is equal to 60 degrees, v is equal to 7.14 meters per second. Now, if I want the velocity, it's this 7.14 14 meters per second along the tangential direction. So it will be along the tangential direction, and it's 7.14 meters per second along the tangential direction. E tangential being the unit vector along the tangential direction. We all agree? Is it clear? Great. So in order to get the velocity, you have to integrate this relationship here, which is extremely important. Okay? Nice. Now, we already calculated the tangential acceleration. It's g cosine theta, so 4.905 meters per second squared. This is the tangential acceleration. And the normal acceleration, we said that it's v60 squared divided by r. We calculate v60 squared, so 50.97 divided by 3. So normal acceleration, you do the calculation, it gives you 17 meters per second squared. Is it clear? Okay, now let me summarize what we found. Velocity 60 is 7.14 meters per second in the tangential direction. The tangential acceleration is 4.91 meters per second squared, and the normal acceleration is v60 squared divided by r. We find it to be 17. Meters per second squared. So we answered question B. Determine the normal force exerted on the particle when theta is equal to 60. We already wrote that. We said that Fn, when we were answering the first question, we said that it was m v squared over r. By v squared, I mean v60 squared over r plus d sine theta. So that means m to 50.97 divided by 3, 9.81 sine 60 degrees. You do the calculation, and you find that the normal force is in the normal direction, and its magnitude is equal to how much? 50.97 Newton. So this is the normal force. Last but not least, determine the angular speed and angular acceleration. Angular speed is theta dot, or sometimes we call it omega. That's easy. How do you get it? You remember S is r theta. That means that V is equal to what? R theta dot, meaning theta dot, which is omega, which is angular speed in magnitude, is V60 divided by r. So omega, which is theta dot, will be equal to V60, 7.114 divided by r. How much is r? 3. And this gives you how much? 2.38 radian per second. And this is theta dot. Next. From here, you know that the derivative of V is A tangential, is R theta dot dot. So in other words, it means that the tangential acceleration that I know already is 4.91 is equal to R, which is 3 times theta dot dot. So the angular acceleration, which is theta dot dot, sometimes we call it alpha, is 4.91 divided by 3. So alpha, which is theta dot dot, you do the calculation, it gives you 1.64 meters per second squared. That's it. So that was all for the exam. You do this, you have full mark, 6 out of 6. I have given bonus point here and there. Okay. Please make sure that you know how to solve this, because this will be very important for the makeup exam. I wish you nothing but the best, and good luck. Peace.